So how do we really know what's true about the human mind? What separates fact from just popular opinion? Today, we're going to decode the science of psychological research. It's the essential toolkit for figuring all that out. Let's dive in.
Think about this for a second. Does that morning cup of coffee actually make you smarter? Or does it just make you do silly things, but, faster? We've all heard claims like these. Maybe you're absolutely convinced your espresso shot sharpens your thinking. Common sense seems like it should be enough to answer these questions, right?
Well, here's the twist. It turns out our intuition, that gut feeling we rely on all day, every day, it can be surprisingly and sometimes even dangerously wrong when it comes to understanding why people do what they do. We're about to see how we go from a simple hunch to real scientific proof.
Okay, so let's start with the problem itself. We all kind of feel like we're experts on people. I mean, we are people after all. But that feeling of expertise, that's exactly where the trouble begins. Our minds are built with these little mental shortcuts that honestly can lead us way off track.
Here's how it works. Let's say you have a hunch about someone, and you turn out to be right. Bam! It reinforces your belief that your gut is a genius. But what if you're wrong? Well, you probably just forget about it and move on. This creates this feedback loop where we only remember the hits and totally forget the misses, making our intuition seem way more reliable than it actually is.
And one of the biggest culprits behind this is something called hindsight bias. This is that feeling you get after the results of a big game or an election are in, and you think to yourself, oh yeah, I saw that coming a mile away. It's the classic, I knew it all along phenomenon. Come on, we've all said this. It makes us feel smart, right? Like we've got some special insight. But the reality is, our intuition is much, much better at explaining what's already happened than predicting what will happen. And that's a huge difference. Think about it, it's a subtle but massive mental trap.
And the mental traps, they don't stop there. We're also just naturally overconfident. We tend to think we know a lot more than we actually do. And on top of that, our brains are basically pattern-making machines. We'll see a hot streak in a series of random coin flips and think it actually means something, when really each flip is a totally separate event. It's these kinds of traps that show us why we need a much more rigorous system.
So, how do psychologists actually get around these mental traps? Well, they use the scientific method, and the very first step is just to describe behavior accurately. Let's look at the 3 main tools they use for just that.
All right, so here are the big 3. First, you've got the case study. This is a super deep dive into one person or group. You can get some amazing insights, but the big weakness? It's really hard to know if what you found applies to anyone else. Then there's naturalistic observation, which is basically scientific people watching. It's awesome for seeing how people really act, but it doesn't tell you why they're acting that way. And finally, you have surveys. They're fantastic for getting a ton of data really fast, but man, they come with their own set of challenges.
And this shows just how tricky surveys can be. A tiny, tiny change in how you phrase a question can have a huge impact on the answer. You ask someone if they support a ban on something versus limiting it, you can get wildly different results. Why? Because words like ban just feel harsher. They trigger different emotions. This is called the wording effect, and it's a perfect example of why scientists have to be so careful.
Okay, so once we've described behavior, the next logical step is to start connecting the dots, right? To see how different things might relate to each other. But this is where one of the biggest and most common mistakes in thinking happens.
Let's go back to our friend Bob and his questionable leftovers. He eats that funky, moldy pizza, and a little while later, he's seeing things. It seems obvious, doesn't it? The pizza and the hallucinations are connected. They are correlated. But did the pizza cause it? This right here, this is one of the most important rules in all of science, so let it sink in. Correlation does not prove causation. Just because 2 things happen together, or one happens after the other, does not mean one caused the other. All a correlation does is predict the possibility of a cause and effect relationship. It can't prove it. I mean, think about it. Maybe Bob hadn't slept for 3 days, or maybe he was already on the edge of some kind of psychological episode and the pizza was just a total coincidence. There could be a dozen other things at play. To figure out the real cause, we need a much more powerful tool.
And that tool is the experiment. This is the gold standard. This is how we figure out cause and effect, because it lets researchers isolate one single factor while keeping everything else under control.
So a real experiment has a few key ingredients. First, you manipulate one thing. That's your independent variable. Then, you measure the outcome. to see what happened. That's your dependent variable. You also absolutely need a control group, the folks who don't get the treatment, so you have something to compare against. And finally, and this is so important, you have to randomly assign people to the different groups. This is how you eliminate bias and make sure it's a fair test.
Okay, let's put this all together and finally get an answer to our coffee question. We're going to move from that vague idea, coffee makes you smarter, to a real testable experiment.
First things first, we need a hypothesis that's clear, specific, and something we can actually measure. Makes you smarter is just too vague, but navigate a maze faster? Hey, that's something we can time with a stopwatch. This is a solid, testable prediction. The caffeine is our independent variable, and the maze time is our dependent variable.
Now we set up our groups. We randomly assign our participants to one of 3 conditions. The control group gets decaf coffee, that's our placebo. Experimental group 1 gets a low dose, like a normal cup of coffee. And experimental group 2 gets a high dose. This setup lets us see if the amount of caffeine actually matters.
So after everyone runs the maze, we get to look at the data. And in these hypothetical results, you see a really clear pattern. The more caffeine people had, the faster they solved the maze. Now, because we controlled for other factors and used random assignment, we can be much more confident that it was the caffeine that actually caused this difference in speed. See? No more guessing.
So, as we wrap this up, what's the big picture here? What's the main takeaway? It's really about developing a new way of thinking, a way to move past our flawed intuitions and get closer to what's really going on.
This is the core idea right here. Our brains are incredible, but they are full of bugs and biases, like hindsight and overconfidence. The scientific method isn't just a list of steps to follow. It's a whole system of critical thinking designed specifically to counteract those very biases. It's how we keep ourselves honest.
So, if you only remember a few things from our chat today, make it these 4 points. First, be skeptical of your gut feelings. Second, watch out for that "I knew it all along" trap. Third, and say it with me, correlation is not causation. And finally, remember that a well-designed experiment is the most powerful tool we have for finding real answers.
And that leaves us with one last thought. We all hold these little beliefs about how the world works, about what makes people tick. So now that you have the toolkit, think about it. What piece of common sense, something you've always believed, might not actually hold up under a real scientific test?